Good afternoon. Welcome to the third series of the NIR Forage and Feed Testing Consortium's webinar series. Today we're going to be talking NIR versus wet chemistry and forage analysis with Dr. Uttam Saha. We are going to wait a couple of minutes to just let some lagging attendees to come in before I introduce Dr. Saha. So in that time, I guess I would point out a few things to those of you that are already here. You're only in listen mode. The only way you can communicate your questions to us is through the GoToWebinar questions. You can type your questions in. After the webinar, we would love to have you reach out to us. So that will be going forward. So if you've been following along with our webinar series, then you know that the first one was about the importance of forage testing. The second one was about some basic understanding of how NIR technology works. So it's very exciting today that Dr. Uttam Saha will be presenting some new data about the repeatability and reproducibility of wet chemistry versus NIR. So with that, I think we should go ahead and get started. If you were coming in late, the attendees are on mute, and you can put your questions, you can type those into the questions in the GoToWebinar, should be on the right hand of your screen. Okay, and so without further ado, I'd like to introduce Dr. Uttam Saha. He is a Senior Public Service Associate, which is the equivalent of being a full professor under the University of Georgia. He, among others, directs the Feed, Forage, and Water Testing Education Program of the University of Georgia Extension Service. He has an extensive experience in research and extension. He works in soil fertility and nutrient management, animal feed and forage, remediation of contaminated soils, production of high-value greenhouse vegetables, and a few other areas. Dr. Saha is the chair of the Drinking Water and Human Health Community of Practice of the National Extension. He has been the co-principal investigator of the EPA-funded State Indoor Radon Grant for the state of Georgia, and he has been serving on the NIR Forage and Feed Testing Consortium's Board of Directors for around 8 years. He is also served on the Calibration Committee for 6 years and is a prolific writer, having authored an impressive 100 journal articles and 25 extension publications. So without further ado, we'd like to thank Uttam for presenting today and welcome him.
Very good. Thank you very much, Becca, for the good introduction. And first of all, I would like to thank everybody for your interest for this session. As you see, I'm going to talk about some comparison of NIR infrared spectroscopy versus wet chemistry in forage analysis. In particular, its accuracy and precision. And I'll talk a little bit detail about the repeatability and reproducibility of NIR versus wet chemistry. So, hope we all know that quality assurance in analytical chemistry is very, very important. And there are two important pillars of quality assurance, which basically evaluate the two types of error we may have in the analytical work. One is precision, another is accuracy. And we know precision is the closeness of the repeated measures. And as the repeated measures are close to each other, then we have less error. And if they're wide apart from each other, we have more error. And these errors related to precision can be defined in two situations. One is the repeatability, which is the measures of error in repeated measures and within a given lab. The other is reproducibility, which measures basically interlaboratory repeated measure error. The second one is accuracy, which is the closeness of the measured value with the true value or consensus value. So let's see how we did in the forage analysis by wet chemistry and NIR. So in this task, what we did here, we actually evaluated the accuracy and precision of NIR versus wet chemistry from National Forest Testing Association proficiency test sample over a period of 6 years from 2013 to 2019. And in this evaluation, we used Forage function, which is the most important function in analytical chemistry when we evaluate accuracy and precision. Let's see what it is. In 1980, Horowitz came and Boyer pointed out that an examination of results of over 50 interlaboratory collaborative studies conducted by AOSC on various commodities for numerous analytes shows a relationship between the mean coefficient variation expressed as powers of 2 with the mean concentration measured expressed as powers of 10. And this relationship was independent of determinative method. That means anything we measure. And such function was originally expressed in mathematical form by the statistician named Jun-King Liu. And you can see here the expression, which is the relative standard deviation in percentage is equal to 2 to the power 1 minus 0.5 log of C. So where C stands for the concentration of analyte expressed as mass fraction. That means if I have a 90% dry matter, the mass fraction will be 0.9. And RSDR, which is the relative standard deviation under reproducibility condition, is actually the CV under reproducibility condition. Later on, Michael Thompson transformed this equation into much easier form. So RSDR percentage equal to 2C to the power minus 0.15. Or it was also written in standard deviation form as 2C to the power 0.85. And if you look at the National Forest Testing Association proficiency test report, you will see a standard deviation called HSD or Horowitz standard deviation. And when we express that thing in percent, it's basically that standard deviation calculated based on that relationship multiplied by 100. And C, in case of the NFTA PT report, is basically the RMA expressed as the mass fraction. So for example, in 95% dry matter, C will be 0.95. So this is a graphical representation of the Horowitz equation, what I described in the previous slide. It is also known as Horowitz horn and was considered one of the most intriguing relationships in modern analytical chemistry. And this slide basically shows the RSD calculated from Horowitz equation with different concentration of analytes, which are marked as different points on the curve in the previous figure or on the figures on the previous slides. As you can see here, as the concentration gets diluted, the predicted relative standard deviation under reproducibility condition increases. And now later on in 2000, Michael Thompson found that precision was overestimated at extreme values of C. As a result, Horowitz equation was further adjusted for different concentration as the standard deviation under reproducibility condition is equal to 0.2 multiplied by C if C is less than 1.2 multiplied by 10 to the power minus 7, whereas standard deviation under reproducibility condition is equal to 0.2 C to the power 0.8495 if the concentration C is greater than 1.2 into multiplied by 10 to the power minus 7 to less than equal to 0.138. As you see here, C is a mass fraction. 0.138 means actually 13.8%. And if the concentration goes above 13.8%, the function will be standard deviation under reproducibility condition equal to 0.01 C to the power 0.5. And with all these changes, the Horowitz graphical representation of Horowitz equation looks like this. So let's talk about the repeatability and reproducibility. If you pay attention to this picture here, you can see there are 3 labs. They have measured something for 5 times or a given analyte for 5 times. So now you can see the types of standard deviation that exist here. You can see the variance or standard deviation square followed by a small r represent the variation due to the repeated measures within a given lab. There is another one which is followed by capital L. There's the inter-laboratory variance. And the reproducibility variance is actually sum of that repeatability variance and the inter-laboratory variance. And the standard deviation is the square root of that. So let's go to the next slide here. So you can see I gave some mathematical relationship how we can calculate some of these parameters relevant to evaluate the precision and accuracy. You can see the standard deviation under repeatability condition is that equation. And the second one is the relative standard deviation under repeatability condition. Third one is the standard deviation for interlaboratory variance. And the fourth line is the standard deviation for reproducibility. Here, K represents the number of labs and N represents the number of measurements done in each lab. And X mean I is the mean value reported by individual labs from the repeated measures. And grand mean is the overall mean derived from N multiplied by K values. So let's go to the next slide here. For the repeatability, we actually evaluate it by a ratio called Forage or Horowitz ratio. If it is followed by a small r, that is a ratio relevant to the repeatability, which is the measured relative standard deviation and the predicted relative standard deviation under repeatability condition. And just for our note, the predicted relative standard deviation is calculated from the Horowitz equation, and the RSD is calculated from the reported concentration by participating labs when the measurements are done in replicate condition. The acceptable Horowitz ratio under repeatability condition is 0.3 to 1.3. A similar ratio to evaluate the reproducibility is done by another same type of ratio, but the relative standard deviation is derived for the reproducibility condition, as I showed in my previous slide. And the acceptable Horowitz ratio for reproducibility is 0.5 to 2.0. So there is a second factor in quality assurance, is called accuracy, which can also be evaluated using Horowitz function by a parameter called z-score. So z-score is equal to, you can see here, the x mean is the mean value of the replicated measurements reported by a given lab, and minus the reference method average, which is basically in this case, in case of National Forest Testing Association, is the consensus values reported by various labs using wet chemistry method, and divided by the standard deviation of Horowitz, which is basically the predicted standard deviation based on the C. You remember that function? C is the mass function, and it is basically RMA is the C. And I have shown you how we calculate the HSD under different condition, and which will be, these two functions will be useful for the parameters we are going to talk, depending on the concentration we are going to deal with. And you may know that as long as z-score is less than or equal to 3.0, the accuracy is considered satisfactory by the National Forest Testing Association, and it is considered as the passing grade. So this slide shows the dry matter content plotted in triplicate reported by 7 NIR labs along with the reference method average and the upper limit and lower limit of acceptance in 33 alfalfa hay proficiency test rounds conducted by the National Forest Testing Association. If you look at this picture, this graph properly, you will see that green line is the RMA. And the 33 RMA values, we plotted and a line is generated. And you see the upper limit of acceptance, which is RMA plus 3 multiplied by HSD. And the lower limit of acceptance is the RMA minus 3 times HSD. And what we see here almost all of the dry matter value reported by the NIR labs are within the acceptance window, and they are even very close to the line of RMA. And this is a robust demonstration of the fact at a glance that NIR is as accurate as wet chemistry. But I will show you some more quantitative measures using G-score later on. So this is the similar plot for the crude protein from the 7 lab reported in triplicate for the 33 alpha-alpha PT round conducted for over 6 years, 2013 to 2019. You can see the crude protein reported by the NIR lab are also within the acceptance window generated by the wet chemistry method reference RMA or reference method average and the HSD. And this is a similar plot for ADF. And you can see this is another similar plot for the NDF. Now let's talk about the NIRS G-score. And you can see here, I was able to actually pull the G-score NIR versus wet chemistry for 4 lab, even though I had 7 lab reported NIR, but I had only 4 lab reported both NIR and wet chemistry. So therefore 4 lab reported in triplicates, 33 PT rounds over 6 years. So what you see here, the plotted Z-score for dry matter are invariably lower than 1, which is very precise, very accurate. And hope we remember the Z-score up to 3.0 will be acceptable to pass the NFTA proficiency test. But here, one other thing I would like to say here, there is not enough clear-cut difference in G-score between the two methods, which is wet chemistry versus NIR, for most of the 33 alpha-alpha PT rounds conducted by NFTA during 6-year periods from 2013 to 19. And this will be more clear in the next few slides, where I plotted the overall G-score for the 4 labs, wet chemistry versus NIR. In these slides, I actually plotted all 4 labs, but I will show some plots for the overall for the 4 labs. You can see here, this is the G-score comparison for overall 4 labs, NIR versus wet chemistry. And as you can see, the G-score did not vary remarkably between the two methods. That clearly indicates that NIRS is as accurate as wet chemistry for dry matter measurement in the alpha-alpha PT rounds we examined. This is a similar plot for crude protein. Here we saw the same thing. This is another plot for the acid detergent fiber. And as I explained earlier, there is hardly any difference between the two methods. It's the same type of plot for the NDF. Let's talk about the quantitative comparison for the repeatability and reproducibility. So this is a plot that compares the repeatability of NIRS versus wet chemistry using the Horowitz ratio. Hope we remember the upper limit of acceptance of Horowitz ratio is 3 for the repeatability condition, but you can see it's way too lower than the 3. So that means both wet chemistry and NIR are really very, very repeatable. But most important thing I would like to point out here is which one is better. If you look at the second axis, which is the right side, is the forward deviation, forward ratio deviation, wet chemistry minus NIR, and which is basically represented by that dotted red line and the points. And you can also see a 0 line for judging the deviation. Here, if the deviation is
Hi, Uttam, I'm sorry to interrupt you. Your slides are not progressing. Do you know?
Okay. I see. Just a second. I'm sorry.
Okay, nope, sorry to interrupt you.
Okay. I think I'm here now. So this 0 line is the dotted line, which basically allow us to evaluate the deviation of forward ratio, wet chemistry minus NIR. If the deviation is greater than 0, or a positive deviation will indicate NIR is more repeatable than wet chemistry. And as you can see here with alpha-alpha diameter, most of the deviation values are positive or greater than 0. That means NIR is more repeatable than wet chemistry. For the 33 PT round over 6 years, we evaluated. And this is a second plot for the dry matter reproducibility. And you can see here the deviation of this reproducibility Horowitz ratio is also positive in most cases. That indicates for dry matter, NIR is more reproducible than wet chemistry. And here I plotted the crude protein for the repeatability with the Horowitz ratio. Here you can also see most of the deviation I plotted is above that dotted line which crosses the 0. That means most of the deviations are positive. And that once again indicate the repeatability of crude protein is better for the NIR than wet chemistry. It's a similar plot for reproducibility. And you can see here the crude protein reproducibility is also better in most cases for the NIR as compared to wet chemistry. And here I plotted the Horowitz ratio obtained from NIR versus wet chemistry for the NDF measurement in alpha-alpha hay. You can see most of the deviations between the two ratios are positive, once again indicating NIR is more repeatable for NDF measurement. This is a similar observation for the reproducibility. NIR is more reproducible for NDF measurement than wet chemistry. The last parameter I would like to discuss is the ADF, and we basically demonstrate here is the same fact. NIR is more repeatable in measuring acid detergent fiber than wet chemistry. And it is another plot for the NIR reproducibility to measure acid detergent fiber. We see here NIR is more reproducible than wet chemistry for measurement of ADF in alfalfa hay. So here is what we saw so far. So this presentation is a robust demonstration of the first fact, which is when NIR calibration models are developed using good science and applied properly, NIR is more accurate. Sorry, NIR is as accurate as wet chemistry in forage nutritional analysis. This presentation is also a robust demonstration of the second fact, which is both intra-laboratory and inter-laboratory precision of NIR method are better than those of wet chemistry. Many nutritionists who are quick to brush off NIRS, citing its poor accuracy, should be pleasantly surprised and change their thoughts by this robust demonstration of similar accuracy of NIRS and wet chemistry, and even better precision of NIRS over wet chemistry for analysis of forages. NIRS Feed and Forage Testing Consortium provides calibration model developed using the best science in the field and ensures its members apply the models properly, which makes NIR as a better option for forage analysis by wet chemistry than wet chemistry. With that, I would like to let you know the contact information of our consortium's executive director, which is here, Patty Moran. Our phone number is here. And I would like to also cordially invite you to join the next webinar, an overview of the NIRS Forest and Feed Testing Consortium, which is scheduled for Thursday, May 21st, 4 p.m. to 5 p.m. Eastern Daylight Time. With that, I'd be gladly answering any question you may have. Thank you very much for your attention.
Okay, Uttam, so it looks like we already, first of all, thank you for that presentation. It definitely is eye-opening, I think, for a lot. So we have a couple questions. The first one, how are you measuring volatile compounds in silage when NIR is used? So as far as the consortium's concerned, as far as volatile fatty acids and things like that, I don't think we have calibrations for them, but if you know better, go for it, Uttam.
I think my answer is similar. We, as a consortium, we don't have a model for that. But some instrument company claim that they have a model for that. Some other thing as well, like non-protein nitrogen in the silages, volatile fatty acids, and others. But to my experience, those models are not as good as we have for other parameters.
Okay, thank you for answering that. So the next question, oh, these are in out of order. What are the main reasons which can explain why NIR can be better than wet chemistry in some cases?
It starts from the how we develop the model and how we apply. If those two are based on sound science, and application standardization is also important, which NIRS consortium basically provide for their members with the documents like our NIRS white paper, standardization of the application, and our training. Those are important ones. Those are in place. NIR basically remain free from several sources of error, whereas weighted chemistry in routine analysis suffer from those errors. Say, for example, technician skill, education training, the purity of chemicals we get in different days, and several other conditions like the health of our instrument equipment, multiple things used like balances, shaker, and other things. But NIRS, once everything done properly and applied properly, it basically remain very, very stable as long as the instrument health is monitored, instrument satisfy the requirement at the beginning of the day, and then there is a less chance of error. Or you can say there is a fixed type of error, which is very, very minimum. Therefore, if we measure this same sample 10 times, we get less error, or the values are more close to each other as compared to the same sample measured by weight chemistry 10 times. And that is what we have presented here, the repeatability and reproducibility. The good thing about this presentation is we basically had the data from multiple instrument platforms like FOSS NIR, Unity NIR, applied in different labs over a 6-year period of time, when same sample in each of the 33 occasions were measured 3 times by weight chemistry and NIR. And we found NIR is more repeatable within any given lab, as well as it is more reproducible between the lab or overall for different labs as compared to weight chemistry, because it is subjected to less source of error once it is established on a good science and applied properly.
Okay, I have another question. What are the environmental standards that need to be in place to get consistent results with NIR?
It's 2 things. I think it has been in our NIRS white paper or in many training, we talked about the temperature and humidity of the room where our NIRS instrument operate. And generally, we keep a temperature and humidity meter in the room. And I just do not remember exactly what are those critical threshold value for the temperature and humidity. But those are the only two factors, environmental factors, that can affect the NIRS scan on different days. And other thing, as I mentioned, all instrument has a standardized protocol for checking the instrument health before we really put the instrument for the routine analysis for the day. And as long as those are met, and then NIR is very, very repeatable and reproducible as well. And especially in our University of Georgia lab, we have some additional quality assurance measurement in place, which is basically based on a very structured protocol using our archived National Porous Testing Association PT sample, for which we know the consensus value came out of the weight chemistry measurement. And a lot of time we basically compare randomly we pick some of the archived NFT PT sample like one corn silage, one alfalfa hay, one grass hay, and run it before we run the routine sample for the day and see whether we still can get same type of results as we reported and as NFTA really assigned an RMA value for that, or passing grade, or that acceptance window, what I showed, whether it falls well under that window or very close to the RMA or not. And if those checks really come out good, then we can be confident that we are good for the day to run our routine sample. Those are some good laboratory practices we follow at University of Georgia. And that keeps us very, very confident that our routine NIR analytical results are sound.
Okay, so we still have a lot of questions coming in. So what are the minimum fit statistics that should be reported for readers of a publication if we use NIR to predict nutritive values of forages, or if we use the NIRS consortium?
Well, it depends on, as I said, if you have a standard sample for which you know the consensus value or reference method average, or which is based on the weight chemistry method, and we compare that with the NIR predicted value, and then we can really compare whether NIR values are acceptable or not. I would say the best tool we have is the NFTA PT sample, and which at University of Georgia we keep those archived, and we generally have that checked, and that makes us very, very confident on the NIR prediction.
Okay, so one additional thing I would like to say about that, if you are using consortium calibrations and you are publishing, you could reach out to Patty or Bobby Joe, and they can provide you with the information you need to properly cite those equations, and that's going to include the year and possibly listing the constituents. So maybe not specific statistics. Okay, so we have another question, and I think we have like 3 more. Comparison with wet chemistry, one must use the same procedures used to develop the model for each element. Is that accurate?
Can you repeat this question one more time, Becca?
So comparison with wet chemistry, one must use the same procedures used to develop the model for each element. Is that accurate? So I think if I were to reword this, I would say if I was wanting to compare my wet chemistry crude protein performance to my NIR, if my NIR was based on a combustion method, I would definitely have to use combustion method to measure the protein to accurately compare those two.
Okay, so I think, Rebecca, you explained this citing crude protein, which is very unique in the sense that crude protein that National Porous Testing Association RMA, or reference method average, is based on a reference method which is basically Kjeldahl. But most of the lab nowadays using combustion end to even report the wet chemistry PT report, proficiency test sample. And that basically correlates or very, very close to the Kjeldahl nitrogen as well. And it cross-checks with the NIR as well. So the Kjeldahl nitrogen, which is the reference method as considered by many feed industries, for the protein correlates very well with the combustion and which also agree very well with the NIR. So the other thing in the, say, for example, ADF and NDF, nowadays we have that Ancom fiber method, but the reference method for those two are the Beaker method. But those also very correlate very, very close to each other nowadays, the Ancom method and the Beaker method and the NIR, which is very, very good. So judging the efficiency or correctness of the NIR is the quality of the equation calibration model. As Rebecca mentioned, the NIRS consortium models are very, very robust, and it has evolved over a long period of time with many revision and doing and redoing. And at this point, the forage analysis by consortium equation is very, very dependable, and the models are very robust. And the statistics for each model and each parameter in various models, we have it available. And those are very good thing to review. As we know, those are really good. And the daily check of the instrument health and some standard sample scanning will really let us do the forage analysis by NIRS without any anxiety or ambiguity about it.
Okay. The next question, are there official or certified samples that NIR users could purchase to check model development and predictions, similar to using peach leaves, for example, when doing protein in forages with wet chemistry?
So far, I know there is no such thing in NIR. So those peach leaf, those are probably NIST reference material, and those are good for wet chemistry. But to the best of my knowledge, NIST does not have any reference plant sample for NIR. Only reference sample we can consider as a reference is the past NFTA PT sample. And this NFTA proficiency test sample, those RMA are based on many participating labs. And if NIR really can make that RMA or the reported value are very close to the RMA or within that acceptable window, I really do not have much anxiety or ambiguity about the NIR predicted value. Therefore, in our lab, in our daily work, or in addition to the instrument health, room environment, we actually run some archived NFTA PT sample and check the predicted results with the historical result.
So currently in the A&Q committee, we are working on revising the guidelines, and I know that you can purchase past NFTA samples as a bulk sample, if that would be something you would be interested in. And that would be from the National Forage Testing Association, not to be confused with our group with the consortium. Okay, so the last question it looks like I have that has gone unanswered. If you have a question and you're still listening and it hasn't been answered yet, just type it in again so I can see it. Why hasn't NIRS consortium moved to analysis of fresh forages yet?
Well, I would let you or another person like Dave may be able to answer this.
Oh, okay. You want me to answer this? Okay. So I know. Oh, go ahead.
No, please go ahead. Is this the question about a standing crop in the field, or is it just fresh forage?
It just says fresh forages, but I'm thinking that might be what he's getting at. So if you have a go ahead. Go for it.
No, you go ahead and answer it.
Oh, a sample coming out of the chopper or the mower. So essentially, I think he's asking why aren't we able to analyze forages without prior drying and grinding?
Oh, I see. I think there are some handy instrument for that. Kind of it can qualitatively give some indication in the field. But for the laboratory method, which is more correct and precise, there is a moisture requirement because water is a major NIRS light absorber. If water content is very, very high, then it generally masks the signal coming from other functional groups of our interest, like crude protein, ADF, NDF, and whatever. So therefore, research shows that the sample should be with dry matter content ranging from 94 to 97%. In other words, moisture content ranging from 3 to 6%. That basically gives us the opportunity to measure all parameters properly, including diameter.
Yes, I think that's a good answer. And I did follow up with him that I will send him some more information once we're off here and I can get to his email. Let's see. It looks like, let me double check and make sure there's no further questions. Okay, I'm not seeing any further questions. I am seeing multiple people wondering if they're going to be able to get copies of these slides. So a follow-up email will be sent out with video. So if there are further questions, go ahead and send them in. If not, then I will be following up with those of you that I said I would. I have one more housekeeping item that I forgot at the forefront of this. So I am the professional animal scientist at Ward Laboratories, and ARPIS, American Registry of Professional Animal Scientists, they are offering credits for this. So if you are a professional animal scientist, be sure for the whole series, it's 2 credits. So make sure you get on and get your continuing education. So I'm not seeing any more. So I'd like to thank first of all, Uttam, our presenter. Thank you, Uttam. You did a wonderful job of putting that data together and displaying it and explaining it in a way that we can all understand the implications. And for all of our attendees, thank you for taking time out of your day to listen to our webinar, and feel free to reach out to Patty or myself if you have further questions. So thank you.